So today we're going to go over and review some basics of acids and bases. We've already talked about this once this year, and you had it in first year. There will be a few newer kind of connections between what we just finished as we go along, but this will kind of give you a background, getting you back into working with acids and bases. So if you remember, the most basic definition of acids and bases was Arrhenius. And Arrhenius said that acids are things that will increase the hydrogen concentration in water. Bases, when they dissolve, are something that will increase the OH minus concentration. HCl and OH are good examples of this. Now, it was a really simple way to identify, but it's also very limited. So there are compounds that we consider an acid or base that do not have one of those two things, and so it was very limited. So Bronson-Lowry was the next definition, or the more broad definition, and Bronson-Lowry said that acids are things that can transfer or donate protons to another substance. Now, protons are hydrogens, so it's donating a hydrogen. Whereas a Bronson-Lowry base is something that can accept a hydrogen from another substance. So when you see the hydrogen, you'll see it written as H+, or you'll see it as written as H3O+. H3O+ is actually the more accurate way because it's basically a water taking on a hydrogen to make H3O+. When we write it, a lot of times we'll just write H+ because it's simpler and it's quicker to write, but you will see both of them, so you want to understand that they are used interchangeably. So Arrhenius and Bronson-Lowry definitions overlapped in many cases. So you have NH3, which is a Bronson-Lowry base, H2O, which is a Bronson-Lowry acid. So Bronson-Lowry acid accepts the hydrogen, and it does cause the OH to go up. So it's considered a Arrhenius base. One substance can't be a Bronson-Lowry acid unless it also simultaneously acts like a Bronson-Lowry base. The acid must lose the hydrogen, and the base must have a non-bonding pair of electrons that can bind with the hydrogen. So here in this NH3, there's a non-bonding pair of electrons there. It'll add the hydrogen, so now you'll get the NH4+. So we have substances that are amphoteric. Amphoteric means that it can act like an acid or a base, depending upon what the reaction is. So in the first equation, water is acting like a Bronson-Lowry base, so it's going to accept the hydrogen. Whereas in the second example, the H2O is acting like an acid, so it's going to donate the hydrogen. So notice in the first equation, H2O accepts the hydrogen and becomes H3O+, whereas in the second one, H2O donates a hydrogen and becomes OH-. NH3 is another example of an amphoteric substance. So when it's a Bronson-Lowry acid, it's going to donate a hydrogen and become NH2-. When it's acting like a base, it's going to become NH4+ on the other side. So in acid-base equilibrium, protons are donated in forward-back reactions. So the two substances in a conjugate acid-base pair differ by a hydrogen, and that acid has the extra hydrogen. So over here, HNO2 is acting like an acid. It donates a hydrogen and becomes an O2-. Over here, H3O+ is going to act like an acid. It's going to donate a hydrogen and become H2O. So strong acids or strong bases, or strong acids are going to be things that easily donate, where strong bases will easily accept. Weak acids or bases do not easily donate or accept the hydrogen. In general, the stronger the acid, the weaker its conjugate base. And so the stronger the base, the weaker its conjugate acid. So again, the conjugate is what's left after. In every acid-base reaction, the position of equilibrium favors the transfer of hydrogen from the stronger acid to the stronger base. So if you're reacting an acid with a base, it's going to drive in the reaction that is going to be the stronger side. So in this case, we have Joe Montana throwing to Jerry Rice. Going the other way would be Jerry Rice throwing to Joe Montana. These are the more favorable situations. So the reaction is going to be driven this way toward the products. Even though reactants can happen, it's not going to happen as strongly. Okay, we have what's called the autoionization of water, which is just water going back and forth. So water will act like an acid, act like a base. One side will give, one side will accept, constantly going back and forth. So the Kw for this, products over reactants, remember these are liquids, so we drop them off, is the hydrogen concentration times the OH concentration. Well, these together will always equal 1 to the negative 14th. So the Kw for water, just like the Kc, Ksp, Kp is just the equilibrium constant for water is 1 to the negative 14th. Notice it is telling you at 25 degrees Celsius, because if we change the temperature, the K value will change. This example is to be taken valid for pure water and for dilute solutions at 25 degrees Celsius. So if the hydrogen concentration is greater than the hydroxide concentration, the substance is considered an acid. If the hydrogen concentration is less than the hydroxide concentration, the substance is considered a base. And if they are equal, then it's considered to be neutral. So if I wanted to calculate the hydrogen ion concentration, if the hydroxide concentration is 2.7 to negative 4th, and then determine if the solution is an acid or a base. So if my equation is that the H concentration times the OH equals 1 to the negative 14th, I plug in what I know, which in this case is a hydroxide, solve for the part that I don't know. Right? So because the H concentration is greater than the OH concentration, the H concentration is less than the hydroxide concentration, it's considered a base. So definition of pH, is the negative log of the hydrogen concentration. So as the hydrogen ion concentration goes up, the pH is going down. So the more hydrogen it has, the less the pH is. To figure out the pH, we take the negative log of the hydronium ion, or same thing as saying the negative log of the hydrogen concentration. So 0 to 7 is considered acidic, 7 to 14 is considered a base, and 7 is considered to be neutral. For one change in the pH unit means that the hydrogen ion concentration and the OH concentration has changed by a factor of 10. So solution of the pH 2 is how many times more acidic than one with a pH of 5? It would be 1,000 times more acidic because you're moving 3 factors. For significant figures for logarithms, we take the number of sig figs in the concentration is the number of decimal places in the pH. So if I want to find the pH of the hydronium ion concentration is 5.2 to the negative 9th, I know the pH is equal to negative log of that value. So I get 8.28. Since the pH concentration, if the pH concentration is 5.2, that's why I have 2 decimal places here. If I want to find the pH of the hydroxide ion concentration is 3.9 to the negative 10th. Remember, that is the hydroxide concentration. So I'm going to plug in, solve for the H concentration, and then I can find the pH by negative logging that. I'm going to have 2 decimals because I have 2 sig figs in my original problem. Other equations that will be useful is converting from pH to, by finding the pH by doing the negative log of the OH. I can go back from the H concentration. If I want to find the H concentration, I can do 10 to the negative pH. If I want to find the OH concentration, I can do 10 to the negative POH. I always want to know that the pH plus the POH is always going to be equal to 14, pH plus the POH. So if I want to find the H concentration, if the pH is 5.22, I would take 10 to the negative of that value. So 10 to the negative 5.22, and I get an H concentration of 6.0 to the negative 6. So you want to just practice with some of those conversions to make sure you're comfortable with calculating. To measure pH, I can use a pH meter, which uses electrodes. I can use acid-base indicators, which will change color depending upon the pH. We can use litmus paper, which just changes color, red or blue. Phenolphthalein is a common indicator. Phenolphthalein is clear when it's in an acid and pink when it's in a base. So depending upon where the pH is going to change will dictate which indicator we want to use. There's hundreds of different indicators. So it tells you right there that bromothymol blue is yellow when it's a pH of less than 6 and blue when it's a pH of greater than 7.6. So if we had something that was going to change within that range, we might want to choose that as an indicator. pH paper is a way that we can also test the pH. So we would touch the substance to the pH paper, and then we match the scale to figure out approximately. We also can use pH meters, which is probably the most accurate way. We'll use the veneer products to help us do it also. Just a reminder, I mentioned this a while ago, but strong acids and strong bases. So you are responsible for knowing the 7 strong acids, the formulas, and the names. So you want to make sure if you have not already memorized those to start memorizing those. Strong bases are considered the group 1 and group 2 hydroxides. So lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium. Those you don't necessarily have to memorize those 8, but you do want to be familiar with them. But the acids you are expected to memorize. So strong electrolytes are written with one-sided arrows. So those are things that completely dissociate. So HNO3, which is a strong acid, is going to completely dissociate and not go back. Same thing with HClO4. It's going to break up into H plus and ClO4 minus. So if I wanted to know the pH of this solution, I can do my little ice chart. So initially, it's 0.012 is the concentration of the perchloric acid. I know that because it's a strong acid, it's going to basically 100% dissociate. So that means everything I had at the beginning is now gone. So because this is a 1-to-1 ratio, for every one of these, I get one of these and one of these. So if 0.012 of this is going to break down, I'm going to make 0.012 and 0.012. Now, you'll see this after a while or quite a bit as we move into acid-base equilibrium. There's some things that we have in the equation that we really don't care about, because if we want to know the pH, we really just need to know the H concentration. Now, the ClO4 might help us to determine that, but we really care about the H concentration. So we would then negative log that H concentration to get to the final value of 1.92. Here's another example. If I have nitric acid, the solution has a pH of 2.66. I want to know what the concentration is. So I can figure out the H concentration, taking 10 to the negative 2.66. So it gives me 2.2 to the negative third. So if I know that I got 1 hydrogen for every 1 HNO3, that means if the concentration of the H is 2.2 to the negative third, the original concentration should be 2.2 to the negative third. Calcium hydroxide, strontium hydroxide, barium hydroxide are strong electrolytes, but they have limited solubilities. It means that if you put a chunk of these in water, a little of it will dissolve, but the little it does will float around as X2 plus and OH minus. So even though very much of it does dissolve, when it does dissolve, it's going to stay. If I wanted to find the pH of the 0.0034 solution of calcium hydroxide, it's going to break up into calcium and hydroxide. So our original amount of the solution is 0.034. I'm assuming, because it doesn't tell me it's different, I have 0 of these. We don't really care about the calcium because we only care about what's going to tell us the pH. So since it is a strong base, 100% of it is going to dissociate. So for every 1 calcium hydroxide, I get 1 calcium and I get 2 hydroxides. So basically this is like saying X and 2X. So that's why this value is doubled. So I can find the pOH by taking the negative log of the OH concentration. So I get a pH of 2.17. So if the pH is 2.17, I know the pH plus the pOH have to equal 14, so I can figure out that the pH is 11.83. Okay, and just another little fact about bases. Metal oxides, hydrides, and nitrides containing oxygen, hydrogen, and nitride, respectively, also will react with water to produce strongly basic solutions. So these are just things that we can, basically what happens is this H2O is going to donate a hydrogen to create these base solutions. So this is going to donate a hydrogen, become OH minus. This is going to donate a hydrogen to become the NH3 in this case, and I get an OH minus. So you'll see these kinds of equations as we move on into acid-base equilibrium. But whenever I have an anion, I'm going to add water, and it's putting it into a basic solution. Right?